So the goal of Taurus is to improve our ability to forecast tornadoes.
3, 2, 1.
The drones enable us to go in and make the measurements where the meteorologists want them, when they want them, and to do that with confidence and the ability to repeat those measurements. My name is Brian Argro. I'm professor and chair of the SME Department of Aerospace Engineering Sciences.
My name is Eric Frew. I'm a professor in the Aerospace Engineering Sciences department here at CU Boulder. The tornado warnings that are issued by the National Weather Service give about 15 minutes of warning time. And the expectation is that with better understanding of the storms, we can push that out to 1 hour notice.
One of the things that's a challenge with the tornado research, with the supercell research, is getting instruments into the storm in places where you can't put humans and you can't use things like balloons and so forth. Remote sensing can only give you so much information.
Claude Shannon, the father of information theory, was deeply inspired by the close connection between entropy and information. he defined a new type of entropy, Shannon entropy. It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation of a random event. In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event. So for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure because his formula was almost identical to the formula for thermodynamic entropy. Just multiply by the Boltzmann constant to get the latter. If you take all possible results of the die roll to be equally likely, then Shannon's formula looks just like the Boltzmann equation. This isn't a coincidence. In fact, Shannon entropy is, in a sense, just a generalization of thermodynamic entropy. The former describes the amount of hidden information in any system. The latter applies specifically to thermodynamic systems. And there's a third, perhaps even more fundamental type of entropy. That's quantum entropy, also known as von Neumann entropy. It describes the hidden information in quantum systems, but more accurately, it's a measure of the entanglement within quantum systems. In fact, the evolution of quantum entanglement may be the ultimate source of entropy, the second law, the limits of information processing, and even the arrow of time.
The point now in these early days is to investigate physical systems of a sort that just haven't existed before. It's to make something that when you see or measure its properties, it's like, wow, atoms have never behaved that way before. Light has never behaved that way before. So the beginning of this is having few quantum things, whether they're electrons or photons or atoms, talking to each other in this quantum language, which if the system is open to the world, there's just too much noise coming in. Imagine you're walking along and trying to have a conversation. So they start talking and boom, in comes a ping pong ball and hits them in the head. And so that constant bombardment disturbs any train of thought about having this conversation in the quantum language. A simple way to think about it is in the quantum world, everything, electrons, are not little BBs, little tiny particles, little tiny bowling balls, but they're really waves. It actually goes up and down, just like a water wave. So if you have a nice, perfectly calm day and you're going to put your finger in and then have the waves spread out perfectly calmly, that's like an electron moving through a solid. But if the wind's blowing, then you get all these other little wavelets that interfere with this beautiful single wave. Well, by the time you're through, you don't see the nice wave. It doesn't have any coherence left. That's famously formulated by Einstein 100 years ago. They called the fluctuation dissipation theorem. If these fluctuations of things coming in to mess up the quantum system, then the atom dissipates its beautiful quantum stuff into the environment. So all you have is just this envelope of energy without the actual waves. And the quantum physics is in the waves. So typically, to have really interesting quantum phenomena, you have to just get rid of all the interactions, all the people out there throwing ping pong balls. You gotta get rid of that.
Entropy is surely one of the most perplexing concepts in physics. It's variously described as a measure of a system's disorder, or as the amount of useful work that you can get from a system, or as the information hidden by a system. Despite the seeming ambiguity in its definition, many physicists hold entropy to be behind one of the most fundamental laws in all of physics. The great astrophysicist Arthur Eddington once said, "The law that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." Eddington wasn't the only one to see the second law as fundamental. As we've discussed in previous episodes, the second law of thermodynamics may be responsible for the arrow of time and is a key ingredient to solving the black hole information paradox, a solution that may one day unite quantum physics with gravity. But despite these clues to the importance of entropy in the second law, it's not obvious what makes it so fundamental. A system's entropy is what we call an emergent property, and the second law seems to be an emergent law. Emergent properties and laws arise from the statistical behavior of large numbers of particles. For example, A room full of air has a temperature, which is a measure of the average energy of motion of all the individual air molecules. But a single air molecule doesn't have a temperature, at least not in the same way. Instead, that molecule has a velocity and a mass and so on, which define how it bounces off the walls or other particles, giving rise to what we perceive as temperature, and giving rise to the laws of thermodynamics. Getting more fundamental means getting quantum, and there is indeed a type of entropy that applies to quantum systems like our air molecule. It's von Neumann entropy, and understanding it may help us understand not just the second law, but also the arrow of time, and how the large-scale world emerges from the quantum world in the first place. Here we start to see the connection between entropy and information. If all the air is in the corner of the room, for example, then you know more about the positions of the individual particles. They're all in the corner of the room, versus if they're spread through the room. But it took the invention of information theory to really see the connection between information and entropy. It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon entropy. Shannon entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. If all the particles are bunched up in the corner, then measuring their exact positions gets you some information, but if you measure the positions when they're spread through the room, you increase your information by a lot more. And this is where we can connect von Neumann entropy to all of the other forms of entropy and glimpse the real origin of the second law. When viewed with its entangled partner, the coin exhibits quantum weirdness like superposition, and that could be revealed in experiments like a Bell test, which we covered previously. But treated individually, each separate entangled quantum coin behaves kind of like a regular classical coin. For example, it doesn't by itself exist in a pure superposition of states. That superposition only appears when you include its entangled partner. It's in what we call a mixed state, heads or tails, not heads and tails, and just like the regular classical coin, it has non-zero entropy. This similarity between the classical coin and the entangled but isolated quantum coin is no coincidence. Its entanglement is the first step in the transition between the quantum and the classical world. Our capacity to observe quantum effects like superposition depends on being able to access the entire wave function. With one partner coin in entanglement, that becomes more difficult. But as a quantum object interacts with the countless particles of a macroscopic environment, and those particles interact with each other, the web of entanglement grows so quickly that it soon becomes impossible to access the entire wave function. We call this process decoherence. It's how the ordinary macroscopic world emerges from its very weird quantum pieces. And for a deeper dive into decoherence, we do have you covered. Looking at it this way, our classical coin is just like our isolated entangled coin, except now we don't have a simple entanglement between two coins. The entanglement is between the coin's countless constituent quantum parts and every particle they've ever interacted with. That network of entanglement is in the superposition of states, heads and tails, but you can't ever access it, in part because you're part of that network. You've already become entangled with the coin and live in the slice of the wave function, the mixed state, where the coin is either heads or tails. The propagation of entanglement leads to our experience of the very unquantum macroscopic world, but it also drives the growth of entropy,